Okay, the next few lessons are about making electricity with cells. The first one being about the electrode potentials. And as you know, in redox reactions, electrons move from one atom to another. And when electrons move, you get electricity, hence electrochemical cells. So our learning objectives for this video lesson are the following. First of all, we want to know and be able to use the conventional representation of cells, i.e. how to draw and represent a cell, common name battery. After we've done that, we want to know the IUPAC convention for writing half equations for the reactions that happen at each electrode of a cell. And lastly, we want to be able to use electrode potentials to calculate the electromotive force of a cell, i.e. the voltage of that cell. You'll probably have noticed that batteries that you have in your house might be listed as 1.5 volt batteries, and that would be the electromotive force or the EMF of that cell. Firstly, let's just consider the concept of electronegativity, which you may remember is the amount that an atom wants to attract an electron. And what we've got here is we've got a periodic table with the numbers in there. Instead of the atomic numbers and the mass numbers, we've got electronegativity numbers. These are numbers generated by a chemist called Pauling. So this is called the Pauling scale. And you can see that the most electronegative element in the periodic table is fluorine. I think you knew that, and that's got a electronegativity reading on the Pauling scale at least of 4.0. So that attracts electrons hugely. And of course, metals, on the other hand, they actually want to get rid of their electrons. They have a small number of electrons in their outer shell, and because of that, they want to get rid of it so then they can have a full outer shell by releasing their electrons. So their numbers, metals numbers, are generally lower than non-metals. So if you look in group 1, for example, you've got rubidium and cesium there at 0.8 and 0.7. So they are very low electronegativities, and sometimes a concept of electropositivity is referred to in terms of those very reactive metals. Now let's just consider copper and zinc, because they are two metals that are commonly used in cells. Now, copper has an electronegativity of 1.9 on the Pauling scale, and zinc has an electronegativity of 1.6. So you can see that copper wants electrons more than zinc does, or at least you can say, because it's a metal, at least you can say that copper minds receiving electrons less than zinc does. And so there's going to be a difference. There's a difference in electronegativity between copper and zinc, and that difference can be used to drive the flow of electrons, probably in this case from zinc to copper. So let's have a look in a bit more detail at making an electrochemical cell and the chemistry that goes on in the electrochemical cell. The chemistry is all about redox equations. That's why this lesson follows the one on redox equations. And so you're going to have both an oxidation reaction and a reduction reaction that's going to happen, and they're going to allow electrons to flow and make electricity. As I alluded to in the previous slide, an electrochemical cell can be made from two different metals, like copper and zinc, for example, that we mentioned, but they need to be dipped in salt solutions of their own ions. So if that was copper, it might be copper sulfate, and zinc might be dipped into zinc nitrate. And they also need to be connected by a wire through which the electrons will travel. And then the two solutions also need to be connected by what's called a salt bridge, which allows the charge to stay neutral. So let's have a look at a representation of a copper-nickel electrochemical cell. Here's a diagram of one. So here we have two half cells. Let me just draw what we mean by a half cell. So this would be a half cell, and this would be the other half cell, and those two together, they make the whole cell. So that's the half cell where oxidation goes on, and this is the half cell where reduction goes on. So let's consider the left-hand half cell first, and as we mentioned, we've got some zinc. So this electrode is just a strip of zinc metal, and it's in a solution of, let's say, zinc nitrate or zinc sulfate, doesn't matter what the anion is, to be honest. And in the other half cell we have the other metal, so this is copper in this case, so it's a copper strip, metallic copper strip, in a solution of usually copper sulfate, which just gives you copper ions in solution and sulfate ions. And then of course we've got the zinc ions in the left hand half cell and the copper ions in the right hand half cell. So as we mentioned in the previous slide when we looked at the electronegativities, zinc is less electronegative than copper, so it's going to release electrons more easily than copper, and that's why the electrons travel in this direction on the circuit. So obviously for electrons to flow we need the circuit to be complete, and so we've got a wire that connects the two electrons, and you can see the wire travels through a voltmeter because we might want to measure the amount of force that's applying to these electrons. And also the other way that the circuit is connected is by this salt bridge here, which is typically just filter paper soaked in often potassium nitrate. So let me just annotate that. You would get potassium nitrate, and that allows the circuit to be completed. Let me tell you why. Let's say in this case you've got zinc ions being created from the zinc metal. Then this solution would become more positive over time, in which case the electrons wouldn't leave the zinc metal because they would be attracted to the positively charged solution. And so what happens is that anions come out of the salt bridge, in this case it would be nitrate ions, come out of the salt bridge and neutralize the extra zinc ions that are coming into solution. And of course the opposite is going to happen here. What's happening here is we've got copper ions coming out of solution and forming copper metal on top of the copper electrode. So you're losing positively charged ions here, and so to replace the positively charged ions you're going to get your positively charged ions coming from the salt bridge, just to maintain the charge. Otherwise, if this solution became negative, then these electrons that we want to travel in this direction would be traveling towards a negatively charged solution, and they would refrain from doing so, and we wouldn't get any electricity. Just going back to the zinc half cell, notice that we have the electrode is made of zinc, and as we've said before, the zinc is more willing to give up its electrons than the copper, so that's what it does. So if the zinc gives up its electrons, the electrons come off towards the copper in that direction, and if a zinc atom has lost its electrons, then it becomes a zinc ion, right? So the zinc ion comes off into solution and stays in solution there. So going back to the electrons come up and go through the voltmeter here and come down and then come onto the copper electrode. And and so the copper electrode becomes negatively charged, which attracts the copper ions that are in solution. The copper ions are positive, they're attracted to these electrons that have come from the zinc, and they come out of solution, and they take those electrons from the electrode. And if a copper 2+ ions takes 2 electrons from the electrode, then of course it turns into copper metal, right? And then of course starts sticking to the outside of the electrode like that, and builds up as copper on the outside of the electrode like that. And so that's how we get our current. That's how we get our current. And one last point about the voltmeter. So the voltmeter is basically measuring the electromotive force, the force that is being applied to the electrons to move around the circuit, right? And that force is coming from the difference in willingness of zinc to give up their electrons and copper to give up their electrons. And if there's a big difference, there's a big force on those electrons. So if there's a big difference in reactivity of the two metals that form the electrodes, then there's a big force or electromotive force on those electrons, and so more electrons will travel around the circuit with a big electromotive force, all else being equal, of course. Okay, what we've been dealing with is one type of half cell that is a metal in a solution of its ions. We've seen zinc in a solution of zinc ions and copper in a solution of copper ions. That's one type of half cell. Another type of half cell is one like this, where you have in solution you have Fe3+ ions and Fe2+ ions. And this time we're going to have a platinum electrode, because an electron has to be a solid that conducts electricity. And if a half cell doesn't contain anything like this, like here we would have just Fe2+ and Fe3+ ions in solution, so we've got no metal ion as an electrode. So if that's the case, then you can use something else, like platinum, for example, as an electrode. And platinum is used as an electrode for two reasons. One is that it conducts electricity. Electrodes have to conduct electricity. And the second reason it's used is that it's inert. It's not reactive. It's not going to take part in any of these redox reactions. So the reaction that goes on here goes on at the surface of the platinum electrode. So at the surface, what can happen is we can either have Fe3+ gaining electrons, write it like that, to turn them into Fe2+ ions, or you can have Fe2+ ions losing electrons to become Fe3+ ions. So obviously if we are gaining electrons, this will be a reduction, or if we're going from Fe2+ to Fe3+, that's going to be an oxidation reaction. And which of these happens depends on what's on the other side, what the other cell is. So if this other cell is less reactive, say with less reactive than iron, then what happens is you're going to get Fe2+. They're going to be oxidized to Fe3+. It can be oxidized to Fe3+. However, if the other metal is more reactive than iron, then the opposite happens. You're going to get Fe3+, being reduced to Fe2+ at this electrode. So an example would be, an example of a less reactive metal than iron would be copper. Right, and an example of a more reactive metal than iron would be magnesium. Right, so if we had copper, you would get Fe2+, changing into Fe3+, and if we had the other cell made up of magnesium, then you'd have Fe3+ changing into Fe2+. And so the electrons would travel one way around the circuit with copper as the other cell, half cell, and they would travel the other way around the circuit if magnesium was the other cell, half cell. So let's understand a little bit more about electrode potentials. And simply, electrode potentials are measures of the amount that a cell, a half cell, wants to either gain or lose electrons, measured in volts. So if let's say we've got a metal in one of the half cell, and if it wants to lose electrons a lot, it's going to have a negative electrode potential, and if it wants to gain electrodes a lot, it's going to have a positive electrode potential. And the scale of that negative and positive gives you an idea of the scale by which they want to gain or lose their electrons. So let's go back to our zinc-copper pair of half cells, and we're going to write a little table out. So we're going to have zinc 2+ ions, and they're in solution, and you've got zinc solid as the electrode, and we've also got copper 2+ ions, and we write the reactions like this in the reduction direction usually. So at the zinc electrode, we've got this reaction going on. We've got the zinc 2+ ions, and they're accepting 2 electrons and making zinc solid. Or the reverse. We'll say a bit more about whether it's the reverse reaction or this forward reaction, but at the zinc half cell that we saw before, it was actually zinc solid giving up 2 electrons and forming zinc ions, as in the backward reaction as written here. But the standard format is to write it as the reduction reaction, as the forward reaction. So the reduction reaction for the copper electrode is written like this. You've also got copper 2+ ions in solution. Let's not forget our little aqueous for the zinc as well. They also accept 2 electrons in the reduction direction, and they form copper solid. Okay, so what we can now consider is the electrode potential. Write a little column heading here for the electrode potential. So experimentally, these reactions have been measured with a voltmeter, and when zinc has been measured, we get an electrode potential of minus 0.76 volts. And when copper is measured, we get positive 0.34 volts. And the negative and positive we're going to deal with in a future slide, but basically you've got to compare it to something, and actually we compare it to hydrogen, and that's where the negative and positive comes from. We'll deal with that some more in a couple of slides time, but for now suffice to say that the negative and the positive give you an indication of which reaction is happening in each half cell. Is it the oxidation reaction or the reduction reaction? So let's write down a couple of rules. It's really the same rule written in opposite directions. So the rule is this: so the more negative write it in shorthand, the more negative electrode potential is the oxidation reaction. Okay, and the other rule is, all right, the least negative electrode potential is the reduction reaction. When we say the oxidation reaction, the reduction reaction, you remember that in one half cell we've got oxidation going on, in the other half cell we've got reduction going on. Okay, so from these two rules we can work out which is which for the zinc copper. So we look at rule number one, the more negative electrode potential is the zinc, and so that's the oxidation reaction, and oxidation is in this direction. So in the zinc half cell, that is the reaction that is going to happen. Zinc solid is going to go to zinc ions in solution. And if we look then at rule number two, the least negative electrode potential, so this is actually positive, so that's less negative than a negative number. The least negative electrode potential is the reduction reaction. And so this is the reduction reaction for copper in this direction. So you're going to have copper ions in solution, accepting electrons from the electrode and forming copper solid around the electrode. And that's what we saw when we studied it. And so there we have a quick rule to allow you to find out which reaction, oxidation or reduction, is happening in each of the half cells of an electrochemical cell. Okay, let's have a look to see how we can draw electrochemical cells. And when we say drawing electrochemical cells, what we don't mean is drawing a diagram. We just mean the shorthand drawing of electrochemical cells. And so let's have a look at an example to illustrate it. You just take the oxidized and reduced species from each of the half cells. In our case, the half cells are zinc and copper again, and we just arrange them in a row. So I'm going to draw it out now, and then I'll explain it later. So we're going to take zinc, and we'll have it as a solid. We'll have a vertical line, and then we're going to have zinc 2+ ions, and they're in solution. And then we'll have a pair of double lines, and then we've got copper 2+ ions in solution. We'll have a vertical line and our copper solid. Okay, so let's explain what each of these elements means. First thing to say is that this is a half cell and this is a half cell. So if you just allow me to summarize, to use HC as half cell. So this is half cell 1 and this is half cell 2. And then what we have to do, there's a bunch of rules that we need to follow. And the first rule is that the reduced species go on the left, at the edge of the cell diagram, that is. So the reduced species go on the edge of the diagram. That's our first rule. And then the oxidized species go in the middle. Okay, so in zinc's case, the oxidized species is the zinc ions, and they go into the middle, which is nearby the double vertical lines, and the reduced species of the zinc half cell is the zinc solid, and so they go onto the left hand side. Now, in the copper case, in half cell number 2, the reduced species is the copper solid, and so that goes on the outside, and the oxidized species is the copper 2+ ions, and they go in the middle. So that's why we write it in this order: zinc solid, and then comes the zinc ions, and then after the double vertical lines we've got the copper 2+ ions followed by the copper solid. That's the order in which we write them, that we've just illustrated with these two blue rules. Okay, so I'm going to switch to green, because then we're going to talk about these double lines here, and so they show the salt bridge. If you remember, in our zinc copper cell, we had filter paper soaked in potassium nitrate, and that was our salt bridge. That, if you remember, it keeps the charges neutral in each half cell. Okay, so then I'm going to switch color again to, I don't know, this color, purple, so that we can talk about this vertical line here. And the vertical line tells us that we've got different phases here. So we're separating different phases. So if you notice, we've got aqueous on one side and solid on the other side. And if that is the case, then we draw a solid line, and if that wasn't the case, we would draw a dotted line. Okay, so solid line means different phases. Sorry, let me just correct a mistake I've noticed that I've made there. It's if they're in the same phase, it's not a dotted line, it's actually a comma. So let me draw a large comma here instead. Okay, so it's a comma for same phase. So if you remember, when we had the Fe2+ and the Fe3+, that would be separated by a comma and not a vertical line. So lastly, notice that we've written zinc as half cell 1 and copper as half cell 2. Why did we do it that way? We could have easily just written it the other way around. We could still have the reduced species going on the edge and the oxidized species going in the middle, just written the other way around. So here's the other rule that we need to remember, and that is you're using the electrode potentials to work out which goes on the left and which goes on the right. And so the rule is that the one with a more negative electrode potential, so the half cell, let's write it like this, the half cell with the more negative electrode potential goes on the left. And another way of looking at that is that oxidation goes on the left. And that's the standard that we use, so that when we see a half cell written in this way, we can work out what's going on in each half cell. So the best way for us to embed this is to look at an example. So let's do that on the next slide. So here we have an example. Let's read it first. We've got two half equations below, and they show the reactions at the positive and negative electrodes of a lithium cell. And what we have is we have the two half equations given there. Lithium plus an electron going to lithium solid, and then lithium reacting with manganese oxide plus an electron going to lithium manganese oxide as a solid, and we're given the electrode potentials of those two half equations. We're also told that a platinum rod is used as the positive electrode, and we're asked to draw the conventional representation of this cell. Okay, so let's go through it step by step. And the first thing that you probably won't know, that you'll need to know, is that we've been given positive and negative electrodes. Okay, and let me tell you that the positive electrode is the one on the right of the cell diagram. All right, so in our zinc copper case, that would be the copper one. And the negative electrode is on the left hand side. And so this is where reduction happens. And on the left hand side, the negative electrode, this is where oxidation happens. So that's worth remembering. I'll go over it again. The positive electrode is written on the right hand side, and at the positive electrode, that's where we get reduction reaction. And the negative electrode is written on the left hand side, and that's where we get oxidation. And one other side thing to notice is that we're calling them positive electrodes and negative electrodes. And the reason for that is that calling them anodes and cathodes can get confusing because you're probably used to anodes being positive and cathodes being negatives, but that's only with electrolysis. When you're looking at galvanic cells, which is another word for what we're using here, it's the other way around. So the anode is the negative and the cathode is the positive. So anyway, let's just stick with the rule that we've written in blue on the left-hand corner there. That's the first thing to notice. And then the second thing to notice is that we need to decide which of these is going to go on the left and which of these is going on the right. So we're going to use the rule from the earlier slide. The most negative electrode potential goes on the left-hand side, and the least negative is going to go on the right-hand side. Right, so that's the first little clue that we've got as to how to write this representation of the cell. So the next thing for us to do then is to write down which is our oxidation reaction. Which is our oxidation reaction. So we know that the lithium ion to lithium solid reaction is going to go on the left hand side, and that's the oxidation reaction. So let's write that down as an oxidation reaction. So lithium solid is going to go to a lithium ion giving up its electron. Okay, so we know that because it's the most negative electrode potential, but in the question it's always written as a reduction reaction, but we know that in that cell, that's on the left hand side, it's going to be an oxidation reaction, and so we're going to write, we're just going to reverse that half equation that's in the question to write it as an oxidation reaction. Okay, so in the same way, let's do our reduction reaction. So we know that the reduction reaction is going to happen at the right hand side, so we're going to use the second half equation, and that's already written as a reduction reaction, right? So we can just copy it down. So the lithium ion in aqueous solution plus the manganese oxide, right, plus an electron is giving lithium manganese oxide as a solid. So now we've written our oxidation reduction reactions down. So then the next step is to write out the reactants and products of the oxidation reaction, followed by the reactants and products of the reduction equation. So our reactants, let's go back to blue. Okay, so we've got lithium, so our reactant, and lithium ion, so our product. And for our reduction reaction, our reactants are lithium ion, manganese oxide, and our product of the reduction reaction is lithium manganese oxide. Next step is to put in our salt bridge between the two half cells. So we've written the two half cells in two different colours, so it's clear where the salt bridge should go. And if you remember, we write the salt bridge as double vertical lines. That's that. And so then the next step after that is to add in the phase boundaries. Let's do that in black as well. All right, so the phase boundary is going to be between the reactants and the products of each half cell. So in the lithium, in the oxidation reaction in blue, we have solid lithium and aqueous lithium ions. So they're in different phases, so we're going to write that as a vertical line. And in the reduction reaction, we have lithium ions and we have manganese oxide, lithium ions being aqueous and manganese oxide being solid, so we can, that plus shouldn't be there, let's just overwrite it. That should be a vertical line to give the phase boundary there. But we also, as products, we have two products here. We have the manganese oxide and the lithium manganese oxide, and they are in the same phase, they're both solid, so we're going to have a little comma in there to separate those. So the last thing to put in here is to remember the platinum rod being used as the positive electrode. Now, because it's a positive electrode, is it going to go on the left-hand side or the right-hand side? Well, from the earlier discussion, you can remember that it's going to go on the right-hand side. And so we draw a vertical line to separate it, and we're going to give the chemical symbol of platinum there to signify the platinum rod being used as the positive electrode. And there we have it, QED. So let's do another example. This time, let's do it the other way around. Let's say we're given a conventional representation of a cell, and it is an aluminium and lead cell. And what we were asked to do is we were asked to write half equations for the reactions occurring at the positive and the negative electrodes. So the first thing you'll remember is that at the positive electrode is on the right hand side, and that's where reduction happens. Remember that from the previous slide. And then the corollary is the negative, so that's going to go on the left hand side, and that's where oxidation happens. And now we can write out some half equations. Shall we start with the positive electrode? So the positive electrode, we've got a reduction reaction, and so that's going to be Pb2 plus, gaining 2 electrons, reduction is gain, gaining 2 electrons, and we always write it as an equilibrium reaction to make lead solid. Okay, so that's the reaction happening at the positive electrode, and at the negative electrode we know that that's an oxidation reaction, and so the oxidation reaction is going to be aluminium metal, and that's going to be making aluminium ions, and you remember that they are 3+ ions, and they're giving up, oxidation is loss after all, they're giving up their 3 electrons. And there's the question answered. Easy as that. So as we know already, each half cell or each electrode has an electrode potential, the amount by which it wants to accept or donate electrons. So that means that the whole cell must have a potential, as it does, and that is given the following symbol. E for electrode, and this is the standard sign. Standard, looks like a tube sign, a circle with a horizontal line through it. That is the symbol for the standard electrode potential. And here we're going to give you a formula for calculating the electrode potential of a cell. Okay, so the electrode potential of a cell is the electrode potential under standard conditions of the right hand side. Take the electrode potential under standard conditions of the left hand side, where the right hand side is the reduction and the left hand side is the oxidation, as you're familiar with already. So if we use the zinc copper cell as an example again, we can work out the actual voltage of that zinc copper cell under standard conditions. So on the right hand side, if you remember, that was the copper, and if you refer back, then the electrode potential of the copper half cell was positive 0.34 volts. Okay, and then we're going to have minus the electrode potential of the left hand side, that was the zinc side, and so if you remember, the electrode potential of the zinc was minus 0.76. Okay, so that just works out at plus 1.10 volts, and that is the electrode potential of the zinc copper cell. It's a galvanic cell under standard conditions. And what you might be given is you might be given the electrode potential of the cell and one of the half cells, and you'd have to work out the other half cell. So you do have to remember that it's right hand side take left hand side, and then after you've remembered that, it's easy because you've got an equation with 3 variables in it, and you'll be given 2 of them, so you just rearrange to find the third one. And we can try such an example if you like. So here is our example. We've got a cell, and it's been given an EMF of plus 2.00 volts. It's an aluminium copper cell, and the standard electrode potential of the copper half cell is 0.34 volts, and it wants us to calculate the standard electrode potential of the aluminium half cell. Okay, so of course the first thing we're going to do is write down our standard equation. So we've got the electrode potential and standard conditions of the cell. It's going to be equal to the electrode potential of the right hand side minus the electrode potential of the left hand side. Okay, which is which? Well, we can see that copper is going to be on the right hand side and aluminium is going to be on the left hand side. So, and we're given the electrode potential of the cell as 2 volts. So 2.00 is going to be this variable. The right hand side is going to be 0.34, and that leaves us with what we require, the electrode potential of the left hand side, which is the aluminium. So we're just going to rearrange this equation. Why don't we add E left hand side to both sides, and then take 2 from both sides. So we rearrange like that, and that's going to come out to be minus 1.66 volts. Done. Okay, as usual, let's just finish off by checking that we've covered off our lesson objectives. And at the start, we wanted to be able to know and use the conventional representation of cells. That's been done. We did that for 2 different examples, and then as well as that we wrote half equations from those conventional representations, so we did that. And lastly, we used electrode potentials to calculate the EMF of a cell with that last formula. Electrode potential of the cell equals the electrode potential of the right hand side, take the left hand side. So we've done that one too. And thank you very much. I hope that's been clear. See you in the next video lesson.